Chemistry. We're moving on to lesson 14 of the Foundations unit, and this is on the octet rule. So the octet rule says that atoms are in their most energetically favorable state when they can fill their valence orbital. Octet means 8. It's called octet because all elements except hydrogen and helium need 8 electrons to fill their valence outer orbital. So noble gases such as helium and neon at the end of each row already have full valence orbitals. So there you see helium. It has a full first orbital with 2 electrons. Neon and all elements beyond helium actually have a full valence orbital when they have 8 electrons, and that's the reason for the name octet. They're called noble because they're like royalty. Other elements want to be like them, and you're going to see how that works in this lesson. All atoms want to be like a noble gas and have a full valence orbital. So lithium, which we see right there on the left side of the second row, could gain 7 electrons and have a full valence orbital like neon, way over on the right side of the second row. That would require lithium to gain 7 electrons. Or lithium can lose its 1 second orbital electron and have a full first orbital like helium. Right there. So lithium could go backwards, in other words. Helium is really the next element to lithium. It just happens to be in the row above, at the end of the row above. But helium has an atomic number of 2. Lithium has an atomic number of 3. Well, the shortest path for lithium to take is to lose that 1 electron in the second orbital and go backwards and be like helium. So there you see it right there. So conclusion, the easiest way for helium to be like a noble gas is to lose 1 electron, that second orbital electron, and have a full first orbital like helium. Lithium will never gain 7 electrons. Think about it. Where lithium is on the periodic table, it has a very low electronegativity. There's no way lithium even pulls in 1 electron, let alone 7 electrons. So there's no way lithium's going to gain 7 electrons to have a full second orbital. Instead, because lithium also has a low ionization energy, that means it doesn't hang on to that second orbital electron very well. It's going to give up that second orbital electron, lose the electron, lose the second orbital, and now it just has 1 orbital with 2 electrons. That is the same electron configuration as helium. So we call that the electron configuration, which you see on your screen. A first orbital with 2 electrons is the electron configuration of helium. It doesn't become helium because helium has 2 protons and lithium has 3 protons. So it doesn't turn into helium. It simply has the same arrangement and number of electrons that helium does, and that's called electron configuration. All atoms want to be like a noble gas and have a full valence orbital. So here we see fluorine has an easier way. Fluorine is the nearest noble gas to neon, which is right next door to it. So there you see the red box popped up over fluorine and neon. So all fluorine has to do is gain 1 electron in order to be like the nearest noble gas, which is neon. So fluorine can have a full second orbital simply by picking up 1 electron. So here comes that electron, and there it goes. So now fluorine has the electron configuration of neon. 2 first orbital electrons and 8 second orbital electrons. Now think about the principles we learned earlier about fluorine. It's in the upper right-hand corner of the periodic table. It has an extremely high electronegativity, so it easily pulls in electrons. So the idea that fluorine can pull in 1 electron is very likely. It's the highest electronegativity element on the periodic table, and so that's very likely to happen, that fluorine will pick up that 1 electron. So conclusion, fluorine gains 1 electron to give it a full second valence orbital with 8 electrons. So alkali metals, alkaline earth metals, or transition metals Boron, by the way, is a metalloid, B, have low ionization energies and more easily give up electrons. So metals which become cations, that's positively charged ions, are shown in green. So everything in green is more likely to give up one or more electrons and to be like a noble gas. So everything in green is going to ionize to become a cation, a positive charge. It gives up electrons, therefore it has more protons than electrons. That makes it a cation, a positively charged ion. Nonmetals have high electronegativities, so they gain electrons. Nonmetals can most easily complete a valence orbital octet by adding electrons. So nonmetals, which become anions, that's negatively charged ions, are shown in blue. They gain electrons, therefore they have more electrons than protons to be like the nearest noble gas. So that's everything over on the right side of the periodic table. Of course, we said that the noble gases there in yellow already have full octets, so they don't want to gain any electrons, so they do not have any, essentially no electronegativity. So the nonmetals in red do not easily gain or lose electrons. So those would be those in the 4A group, starting with carbon at the top and then going down to silicon, germanium. Those could either, when you count, they could either gain 4 electrons or lose 4 electrons, but they tend to not do either. They tend to just not ionize at all, neither gain nor lose electrons. So nonmetals in red do not easily either gain or lose electrons. They do not ionize. Noble gases already have full octets, as we just said, and do not gain or lose electrons. So now we're going to take a walk along the second row of the periodic table, starting with lithium and going across to neon. We're going to look at all the elements there. It's a little bit repetitious, but repetition is good when you're trying to learn something. So let's go through this. So there you see some of the elements of the second row of the periodic table. At the end, you see neon at the end of the second row, and up above it at the end of the first row is helium. So let's take a look at this. So lithium can complete an octet by filling its second orbital. This would require adding 7 electrons. Since lithium has a low electronegativity, meaning it's not going to pull in electrons at all, not even one, this would be impossible. So lithium will never gain 7 electrons. So I want to be clear, some students were confused last year. Lithium will never do what you're seeing there. It's just showing one possible way it could gain an octet, but it's not really possible. It can't do it this way. It will not pull in 7 electrons. So what's the alternative? Well, we mentioned it before. It is easier for lithium to give up its 1 second orbital electron as well as the second orbital. This means lithium would have a filled first orbital, the same as helium. So there you see lithium over there. It lost its second orbital electron and its second orbital. So lithium loses 1 electron, giving it a 1+ charge. When we talk about charge numbers like this, we usually put the plus or minus sign after the number, although that's not really important. So there you see lithium having lost an electron. The electron configuration looks just like helium in the row before. First orbital, 2 electrons. Again, lithium does not become helium because lithium has 3 protons and helium has 2. Beryllium, right next door to lithium, can complete an octet by filling its second orbital. This would require adding 6 electrons. Again, since beryllium has a low electronegativity, this would be impossible. So beryllium is never going to add 6 electrons to be like neon over there on the right. Beryllium will never gain 6 electrons. It is easier for beryllium to give up its 2 second orbital electrons as well as the second orbital. This means beryllium would have a filled first orbital, the same as helium. So beryllium loses those 2 second orbital electrons, and that gives it a 2+ charge. Beryllium has an atomic number of 4, and now that means 4 protons. Now it only has 2 electrons, so that means it has a 2+ charge. So what you'll notice in general as we go along this is that atoms go to the nearest noble gas. In the case of lithium and beryllium, lithium had to move one space backwards to helium. Beryllium has to move two spaces backwards to helium. So that's the direction they're going to go in. Boron. Boron can have a complete octet by filling its second orbital. This would require adding 5 electrons. You see boron right now has 3 valence electrons. It would have to add 5 more to have 8. Since boron again has a low electronegativity, this would be impossible. Boron will never gain 5 electrons. It is easier for boron to give up its 3 second orbital electrons as well as the second orbital. This means boron would have a filled first orbital, the same as helium. So watch the boron atom there, and those 3 electrons are gone. So boron loses 3 electrons, giving it a 3+ charge. And again, you'll notice it now has the same electron configuration as helium, 1 orbital with 2 electrons. So if you looked at boron on the periodic table, it loses 3 electrons to go back to be like helium. Its other option was to gain 5 electrons to be like neon. It's never going to do that second option. So it's shorter. The shortest path for it to become like a noble gas is to go backwards, is to lose the 3 electrons and go back to helium. Now, carbon can fill an orbital by gaining 4 electrons or losing 4 electrons. But as we said earlier, generally carbon does not ionize. So it's not going to do either of those things. It's just simply not going to ionize. Now we're moving over towards the right side of the periodic table. We're going to start with nitrogen. So find nitrogen on a periodic table, and you'll see it's moving towards the right side. So nitrogen can have a complete octet by giving up electrons as lithium, beryllium, and boron did. This would require nitrogen to lose 5 electrons, so it has a full first orbital identical to helium. But nitrogen will never lose 5 electrons. It has a very high ionization energy, or relatively high ionization energy. It's not going to lose usually even 1 electron, let alone 5. So nitrogen is not going to lose those 5 valence electrons that you see there. It is easier for nitrogen to add 3 electrons, giving it a filled second orbital. This creates the electron configuration of neon. So again, watch the nitrogen. We're going to add 3 electrons to it. So nitrogen gains 3 electrons, giving it a 3- charge. Again, just count how many spaces nitrogen has to move over to get to neon. It's 3 places: oxygen, fluorine, and neon. That's shorter than going backwards and losing 5 positions to go back to helium. So nitrogen is going to move to neon, the noble gas, in its own row. Let's look at oxygen now. Oxygen can have a complete octet by giving up electrons as lithium, beryllium, and boron did. This would require oxygen to lose 6 electrons so that it has a full first orbital identical to helium. But oxygen has a high ionization energy. It does not give up electrons easily, so oxygen will never lose 6 electrons. That possibility will never happen. It is easier for oxygen to add 2 electrons, giving it a filled second orbital. This creates the electron configuration of neon. So again, watch oxygen, and there we add 2 electrons to it. So oxygen gains 2 electrons, giving it a 2- charge, and the electron configuration looks exactly like neon. Finally, fluorine. Fluorine can have a complete octet by giving up electrons as lithium, beryllium, and boron did. This would require fluorine to lose 7 electrons so that it has a full first orbital identical to helium. Fluorine is never going to do that. It has an extremely high ionization energy. You can't take electrons away from fluorine, so it's never going to lose 7. So instead, it is easier for fluorine to add 1 electron, giving it a filled second orbital. This creates the electron configuration of neon. So a little bit repetitive, but I want you to see this pattern. So in the first 2 columns of the periodic table and the last 6, it's easy to tell what the charge number will be. The middle ones, the ones in the middle of the transition metals requires a table, and we'll show you that in just a moment. So fluorine gains 1 electron, giving it a 1- charge. So this table shows the charge on the ions created by each element. So you have this table in your reference packet. You should review it. Again, if you look at the second row, you see lithium is a 1+, beryllium a 2+, boron a 3+, carbon doesn't have any number above it there, nitrogen is 3-, oxygen 2-, fluorine 1-, and neon has no number because it does not gain any electrons. So you'll note you should be able to figure out the elements in the first 2 columns of the last 6 based on what we just talked about. If you look at the transition metals, however, and even if you go down to the lanthanide and actinide series, which we never will, but look at the transition metals, you'll notice that many transition metals have more than one charge number. For example, we'll go over some examples here in just a second. For the transition metals, you're going to need this table. For the alkaline earth metals and the non-metals over there on the right, you don't need this table, but it's there if you need it, if you want to use it. So let's look at some examples. Iron can lose either 2 or 3 electrons, giving it a 2+ or 3+ charge. Now you may ask, how do you know? And the answer is it's just in the context of the problem. Either you'll be told that, or there's a way that you can figure it out if you don't know. You'll see that as we get further into this subject. Here's another example. Copper, Cu, can lose either 1 or 2 electrons, giving it a 1+ or 2+ charge. Another example is tin, Sn. Tin can lose either 2 or 4 electrons, giving it a 2+ or 4+ charge. Remember, we mentioned that the abbreviations for the elements don't always seem to match their names because many of them are either in Latin or Greek. And finally, we'll look at lead. Lead can lose either 2 or 4 electrons, giving it a 2+ or 4+ charge. So you use this table definitely for the transition metals, and you can use it for the other elements on the periodic table as well. Okay, this is an excerpt from another sheet that you have in your packet. It's called the 60 common ion sheet. And these are the top 2 tables. There's 4 tables on that sheet in all. And so you can also use this to look up charge numbers. The table that's really the most helpful is the one down below. What the last sheet showed you, the charge number by ion sheet on the last slide, was every single element on the periodic table. What this sheet shows you are some compounds. For example, sulfate, SO4, and it shows you what the charge on sulfate is, which is a 2- anion. So that's what this sheet is more helpful for. So you can use either sheet or use them in combination to find out the ionic charges. And that takes care of this lesson on the octet rule and how charge numbers are determined. You will do that quite often in this class. It's pretty easy, and we'll do some exercises today on that.